Okay, yeah, so today I'm going to talk about multipliers because, again, you can just literally write multiply, right? But your debug, it's not your debug core, sorry, that's what I'm preparing for the second half of this lecture, so it's on my mind. But your FPGA has some limited number of multipliers built into it, right? Because multiplication is a really important operation that we're going to do for a lot of things, and it turns out the multipliers are kind of complicated. So it's possible to actually run into an issue where you run out of onboard multipliers, right?
Is multiplication and division like the same level of complication?
Division is more complicated. In fact, I don't even think I'm going to talk about division in this class because writing your own is a nightmare. Division is just hard to implement. But multiplication is hard unless you use a couple of nice tricks that I'm going to talk about. And so that you could sit down and you could design your own multiplier, which is what you're actually going to do in one of your assignments. And you may want to do it sometimes specifically because you want a particular kind of multiplier, right? The nice thing with the onboard resources is they tend to be very optimized. It's to be very fast and power efficient, but they're limited, right? And so sometimes maybe you want to make sure that you're reserving those onboard resources for more important operations, and you want to go program just a simple multiplier that doesn't really care if it's fast, for example, right? It's like how with the ripple carry adder, for example, if you don't care how fast it is, it's pretty simple, straightforward. You string a bunch of full adders together and you have a ripple carry, but it has the propagation delay of all of the full adders summed up, right? So if it's 32 bits, then it has a propagation delay of 32 full adders, which can be a very long time, so it's not fast. Well, multiplication, fortunately for us, is mostly just addition, right? We just add something a bunch of times over and over and over again. But we can simplify this further. So let's start off with just an example. And we're going to multiply these two numbers. Now, the first thing that I'm going to point out, just so that we're on the same page, the top number is the multiplicand. The bottom number is the multiplier, okay? So when I reference these terms, that's what I'm talking about. Now, if we were to multiply two numbers in decimal, right? This is the easiest example where I just go 7 times 3, right, is 21. And I'm going to have this carry issue that I'm going to have to deal with. And then I do 7 times 1, right, which is 70. And that just comes down and I add the carry, right? And then if I want to repeat the same thing and say it's 17 instead, so this is 70 plus 2 is 91. Hopefully I did my multiplication right. Then if I go to this number, right, and I go 1 times 3, this is not really 1 times 3, right? It's 10 times 3. So the 1 just goes here. And then it's 10 times 10. Essentially, right, which is another 100, which goes there, and then we start adding these up and we get the final answer, we hope, right? I may have screwed this one up. I'm not really good at long multiplication because it turns out the longer you've not done multiplication, the harder it gets. Is this right? I don't know. It's on a calculator. I have a calculator I can pull up. 221?
Oh yeah, 1 times 3 is.
Oh, 1 times 3 is 3. Ah.
We can do calculus, we can do easy math.
I'm a partial differential equations. Anything below that, I forgot. So my sensors class, I'm good because that's all PDEs, but this one I'm a little rough on. Okay, so addition, that's the problem that I have. 221. Well, it turns out that just like addition, multiplication is the same thing when you go to decimal. It just gets easier, right? Because I do 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 1101. Well, if I move over to the next one, guess what? It's just gonna mirror this number again, right? Because it's either that number or it's 0. I only have 2 choices. It's either that number or 0. And then it turns out it's just that number shifted by 1.
So why is the leftmost one a 1?
This one, because now I'm 1. So the first time I'm 1011 plus 1 times, which is really 2, right? This is the next position over, times 1011. So it's the same number, just shifted over by 1 decimal, just like this 1 times 3. Well, then if I want to add those up, I can. 1, 1, 1, 0, carry. 1 plus 1 is 0 to carry. Okay. But we need to keep going. We have a 0. Step 4, it's shifted over again, a 3rd spot. So now we're in this column for 0, 0, 0, 0, right? Because it's just not that number. Add up, nothing changes, so I'm just going to ignore it. We're going to shift over one more time. And now we have the 1 again. And so we just start 1 spot over and do 1, 0, 1, 1. Add those numbers together, we have multiplied. Turns out multiplication is really easy conceptually, right? In binary, because there's only 2 options. Either it happens or it doesn't. So these intermediate steps are the partial products, okay, is what they call them. When I put the partial products, then I can take the sum of the partial product and then do it again. So what's cool about this is now we can start seeing essentially just going through this one time, we can start seeing something that looks like an algorithm that we can take advantage of in order to kind of optimize our multiplication. So the way we're going to do that is pretty cool, actually. So we need to keep track of these additions, right? So I could build a circuit pretty easily that just does this, right? And just do kind of a truth table that is like an 4 by 4 truth table, essentially, which would be really obnoxious. Or we can take advantage of this kind of algorithm that we can see developing. And what we need first then is something that if you took 2700 from me, you will be quite familiar with. If you didn't, if you had it from Larry, especially, this is, who knows if you learned this or not. We need something called an accumulator, okay? The accumulator, its whole job is to accumulate some numbers, right? Keep track of these things that we're adding, okay? And then we need to be able to add some numbers, but we never need to add more than 4 at a time, right? So we can really just go ahead and make a 4-bit adder. And then this adder is going to throw things into the accumulator as well as pull things out of the accumulator. Okay? Because if it's in here, I need to pull it out and then add it and then go back ahead. I'm actually off center by 1. I think that's all I need. Okay. So it turns out if you have 4 times 4 numbers, you need 8 bits to store the result, right? And then, so we're going to have an 8-bit accumulator. This accumulator is going to eventually be our result, right? We're just going to keep adding things until we get our result. So what we're going to do is take advantage of the fact that I only need a 4-bit adder, so this keeps it relatively simple. And then we're going to put in into this side, we're going to put in I'm going to just write it this way, mcand. The multiplicand is going to add into this adder. Really just the mcand times the contents of the accumulator is really what we're doing, but we don't have to multiply them. We're just going to add them or not, right? The choice is add or don't add.
What did you say the mcand was?
That's the multiple.
Yes. Sorry, multiplication just gets really long to write, so I'm going to write mcan. All right. So now what we're going to do is we're going to start with the addition, and it might be easier to initially start thinking this way and moving the adder. We're actually just going to hold the adder still, and we're just going to shift the contents of the accumulator. Exactly. So what is nice is that, oh, I do need one more. Sorry, I erased it. I don't actually need it. So there's 9, just because, well, think about it, right? Because if I have 2 times 2, I don't end up with 4. I could end up with 1 more with a carry out situation, which is fine. And the other reason I want 4, right? We can just throw away carry situations, which we do with adders all the time, right? Just be like, oh, it's overflow, too bad. But in this situation, we would need a register normally for the multiplier, right? So we'd have some multiplier that's going to go ahead and do it. It turns out we can just use these 4 to start, right? Because this register is going to start at 0. We don't really care what the results are. And so I'm just going to throw in 1, 0, 1, 1. I'm going to throw my multiplier in here. And what's nice is once I multiply by this one, I don't care anymore, right? I'm done with it. So as I mentioned, I'm going to shift. So I'm going to shift and it's going to get thrown away. And then I'm going to have these results. It's going to move over. This guy's not going to change. This guy's going to be gone, and we'll just step through until this one is all gone. Okay. And then it's just a question of using this bit, whatever is here, to ask the question or answer the question, should I add and then shift, or should I just shift? Yes. So we're going to have a controller. Controller, right? So actually, I'm going to leave this open for just a little bit. Right, so we're familiar with this idea of data path and controller. This is our data path, and then we have a controller to tell it what to do. This is fairly normal for any FPGA, well, digital logic design, right? And it's going to have signals that are add and shift. It probably also needs something like a load just in case, right? It's going to come down to the accumulator. Then it's going to have this add signal that's going to come into this system somewhere, and then it's going to have a shift that goes probably down to, to the accumulator as well. Because this adder is just combinational logic, okay? It doesn't need to do any thinking. It just takes whatever the mcand is and throws it into there. All right. We also need a clock, but I'm not going to draw it, right? Because the accumulator is going to be clocked, so the clock cycle, it knows when to store something into this, because the accumulator is going to be built out of D flip-flops, right? Okay, so we don't have to worry about this controller just yet, so let's focus on the functionality here and kind of think what's going to happen, right? So we look here, we have a 1. So initially we have a bunch of zeros stored in here, so it doesn't have to do any addition at all. So it takes the mcand, which is 1101, and adds it to 0, right? It's going to pull these zeros out, add it together, and then stuff them back in, and just end up with 1101. Okay, that's all. Then we tell it to shift. This one gets thrown away. It's going to shift to 0. It's got to have something. And if we shift it into 1, we'd have a problem. So now we have 101. That's just the left of this, right? And there's a slight chance I screwed this up and it needs to be mirrored, but I don't think so. I think we're okay. And then we're going to repeat the process, right? So I have supposedly in this situation, I'm going to be adding a 1101 to a shifted version of the 1101. And so your process is going to just sit and step through that over and over and over again. And by the time we get to a count of 9, we're done. We've added it up. And I'm going to show this in VHDL because it's going to be easier and cleaner than me erasing and rewriting and erasing and rewriting, right? So we can think about this as a state machine, right? I really like state machines. State machines are your friend. And we can start out with a big complicated state machine, right? That is just going to ask the question, add or shift. So we're going to start in some initial state that is basically we hang out here as long as not start, okay? We don't have a start, so this is start is going to be an input to our controller that says, hey, go multiply these numbers, whatever they happen to be. This load signal is going to have to load zeros in here and the multiplier here and the multiplicand into some register. It needs its own register, okay? And then if it gets to start, then it's going to go to essentially some start state here. The start state doesn't have to be complicated at all, but really, realistically, it's just going to load things into the signal. And so I can do this as a melee state machine, right? So this load signal goes out here and it also goes down into the mcand register, right? That takes whatever my X and Y inputs are and stores them. X goes here, Y, or sorry, X goes here, Y goes there. I have to split it up. Okay. And then we can start doing the add and shift multiplication where we just basically make a decision that if I have M, which I'm going to call this M, okay? And I'm going to multiply. And I assert add. And if I add, then after I add, I need to shift over. And no matter what, I'm going to shift, right? That's what that dash means is I don't really care about what the inputs are. I just want to shift. Then next, if I have 3 here I just shifted, I can just skip, right? If I didn't want to multiply because I had a 0, then I will just shift. So this path is add shift. This path is just shift. Well, guess what? If I just take this 3-block pattern, add 3, 4, 5, shift, over and over and over again until I have what I want.
Could you clarify the transitions like from 4 to 5? What does it mean by the dash?
Dash is no matter what. I don't care what the input is.
So once you're in 4 or state 4, you
Yeah.
immediately go to state 5.
Yep. So I add. So I CM, I add, and then I shift. But I do it this way because I want to make sure that I add and then shift, right? Because there's some delay in my adder. And that's going to determine how fast I can do this. What is my maximum clock cycle? This is the delay through this 4-bit adder. This 4-bit adder could be, you know, it could be ripple carry adder if it's slow, or if I want it to be as fast as possible, then I'm going to do, you know, something like a carry look ahead adder. Copy this model, stick it around until I have 4 bits. Okay, it turns out that's not exactly the best way to do this, right? Because anytime that we see that we're just doing something over and over and over again, we probably can just design a state that just makes a decision and counts, right? This is the same kind of thing that I had you guys do in your UART, which is where instead of having one state for every single bit, you just count, right? What is my bit index? And if the bit index is not done, then you stay in the state and do it again. If it is done, then we go back. This state machine becomes something kind of interesting. Let me just draw it and then I'll talk through it. All right. Oh, one more. Okay. So K, new variable, right? K is just your count. What is my current index in the accumulator? And then is this really just the result of, am I done counting? Okay. Same idea. If I don't have start, I hang out in 0. If I get the start signal, the controller should assert the load signal so that I pull the load in. And then I go into state 1, right? And this is going to be the same kind of decision where if I'm not done counting and I'm not M, let's just shift, right? So if this bit here is 0, just shift it over because we don't add anything. If we're not done counting, sorry, if we have M, we want to add something. If M is true, let's add, jump down to 2. Then once we're in state 2, we make the decision again. Are we done counting? No. Shift. So add, shift. Okay. This one is just shift. This is add shift. Okay. And then we have finally the exit conditions, which are done counting. That's the only thing we care about. Otherwise, we're going to be either just shift, shift, shift if we have zeros, or if we have a 1, add shift. So if we have 1, 1, 0, 1, it's add shift, shift, add shift, right? 1, 1, 0, 1. If I'm done counting, that's this K. Depending on which state I'm in, both need an exit to this done state. The only thing this done state is take one beat to assert done. This done is 1 clock cycle of a signal that says done, move on, right? Okay. So this, which becomes a big mess of, I think, like 14 states or something by the time you're done, becomes 4, which is really nice. And once you can figure out this kind of algorithm approach, which I could make you suffer through if I wanted to, and figure out, hey, reduce this to 4 states. But instead I'm just showing you because this isn't really DSP, right? That's kind of what DSP would be about, is algorithms. But it's always important with VHDL to keep in mind that this is the kind of thing that we're working towards, right? Is coming up with simple ways of solving complex problems. That's our goal. All right. Now, hopefully, I'm going to be able to turn on this projector here and show you the code for this. And then walk through it. Come on, this work. Okay, so I know it's not this one because this. That's just this desktop computer. Is thinks it's nothing.
Your laptop was flashing.
On this one.
Yeah.
Okay. That's promising-ish. That should just be the laptop signal. Okay, display settings. I may be handwriting some code, which is always fun. Yay, okay, fixed it. All right. I'm gonna flip these lights so that you guys can not fall asleep. Okay. So just so we have a nice clean picture, this is book page 215. I like to walk through this just because there's this book. I could have just had you go read this, but it turns out interpreting the accumulator thing is really complicated if someone doesn't tell you how to do it the first time. So anyways, this is that 4-state machine that I was talking about. So if you need to go back and you need to check your notes, it exists in here. This is just talking about the state for the add shift controller, right? So in this case that we have two things actually. We have a controller state machine and we have a add shift state machine, right? Where the controller is just waiting for this command. This just results in what we call linked state machines, which I've mentioned before, right? Oftentimes we have state machines that depend on each other. In fact, you've already made one of these because lab 1 and lab 2, which is where you built a UART receiver and transmitter, they had to talk to each other, right? So the receiver would tell the transmitter when it's done, and that would cause the transmitter to send something back. That's all linked state machines are. They're not that complicated. So let's go peek at the code. This code turns out to be fairly complicated itself if you're trying to walk through it yourself. So I want to do that for you instead of just being go read this. They're using this numeric bit, which is a little bit obnoxious, but that's how they're going to use it. So just like us, process on a clock. Oh, this is actually a cool bit of code right here that you guys can use for various things. Alias, okay? Alias is saying that I want to call this signal M of a type bit is accumulator at 0, right? So instead of having to write ACC as 0 every single time, now you can just write M.
Instead of making like a signal N and then
assigning, yeah, it's very similar to writing signal M and then somewhere inside of the begin writing signal M that gets assigned to ACC at 0. This is just one line of code to create an alias It's kind of like a variable that is linked between the two. This one it simplifies it a little bit later. So then we're going to just go into a state machine, and we have the obvious if start is 1, right? And this is going to need to load things. So this one is not going to explicitly have the two different controller and multiplier, right? Because there's some, you could write it that way, but this one is just going to combine those two. So the if start happens, the big bits of accumulator reset to 5 zeros. Okay. The smaller bits pull in the multiplier, where the multiplier is one of the inputs, right? I called it X or whatever. So it pulls it in and it says go into that first state. Now this is a different one than you've probably seen, which is why I like this one. When we're in states 1, 3, 5, or 7. Okay, so they're actually, instead of using this simplified terminology, they're going to take the advantage of the state itself as the counter. Okay, so you could do this with a counter and just have two states in here for state 1 and state 2, but instead they're going to combine the counter and the state. So we always enter here, and it first asks the question, is M1? If it's not, I'll start here, then we just throw a 0 in, and we, to the left side, right, we're going to throw in a 0, and we're going to concatenate that with 8 down to 1, right, which is just, notice that it's not 8 down to 0, it's 8 down to 1. So we're putting a new 0 on the front, and we're throwing away the least significant bit of our multiplier, just like we talked about, right? However, if M is 1, then the big bits, the highest 5, get assigned to 0 and 7 down to 4 plus the mcand.
Is there not like a shift right?
There is. So the book actually calls this straight out, is instead of doing this operation, you could use shift right logical, SRL, right? Like, the logic operators are something that I pointed out like several weeks ago now by this point. But there's shift right logical, which shifts it right and shifts in zeros. There's lots of different ways to shift, right? You can shift and around, you can shift ones in, etc. This is, we just want to shift in zeros. This is one way of doing it. You can also use SRL. Okay. So if M is 1, add the multiplicand, right? We don't have to do anything else. We're just going to add the mcand and increment the state by 1. Okay. So if we go from state 1 to state 2. So this is the add state, the 1, 3, 5, 7, and the 1, 2, 4, 6, 8 is the shift. So remember that if we just shift, we don't need to add. So we're going to add 2 to our state. So our state is a counter now. So if we're state 1, we add 2, we're back in 3, and we ask the question again. If we need to add, then we jump down to this 2, 4, 6, 8. So we add and then shift and then come back. So that's why the state equals state plus 1. So they're using state as an integer instead of like this enumerated type, right? So up here, if we go look at state, is an integer with a range 0 to 9. And then those just repeat, right? If it's a 1, we add and then shift. If it's a 0, we just shift. Finally, when we get to state 9, state goes to 0. We're done, right? That's our counter. Now, the nice thing is here, and I've shown some of you this, and I wanted to call this out explicitly. It tends to be good. I love doing this, pulling out anything that can be combinational logic, make it combinational logic. So notice this is after the end process, right? Where done, that output signal that says something, tells the external portions of things that the multiplication is ready to be used. The done is 1 when the state is 9, otherwise 0. Now, this is better than doing it in each state because I could write done is 0, so on and so forth, but I have to make sure that I put that done is 0 in every single state. And if I split it out into an if else, then it also needs to be in every single if else, right? Because if I don't, that's saying that I don't care. So every signal that you assign inside of a state needs to be assigned in every single state. Okay, I want that to sink in. Anything you assign in a state needs to be assigned in every state. Because otherwise the state that it's not assigned in doesn't care. Now, like 98% of the time, it won't matter. It will hold on to whatever the last value was and it'll do what you think. 2% of the time, well, let me say it this way. 1% of the time, it will just not work and you'll catch it in your simulation. And about another 1% of the time, it will simulate correctly and not implement correctly. Which that last part, there's this tiny percent chance that happened, but I've already seen it happen to someone in this class where it simulates correctly and implements wrong because when it gets to synthesis, it goes, oh, you don't care what value this is in this state, so I'm going to assign it to zeros instead. And then you think you're, for example, accumulating, and instead you're resetting your accumulator in the middle of something. It does happen. I've seen it happen to one student in this class. So be aware of that. So by moving it out and making it combinational, I don't have to write it a million times. I like to do this in like the ready signal, for example, right? This is exactly the ready signal of your current project of the I2C lab. You could do this with, you could do it with really any of your outputs can be done this way, just when, and you can do when state is 9, else if, or well, just whens, right? When 0, when 1, when 2, else, whatever. And also don't forget to include the else condition, right? If, else, if, else. You always want that else. And in the state machines, and this is super obnoxious, you want to have a when others statement unless you have fully enumerated the case, right? So this integer in their case is defined from 0 to 9. They have specifically enumerated every possible value of 9. But if you are using 5 states, that requires 3 bits, right? If you've used an enumerated type, like we most often do. So the enumerated type, if you use 5 states, requires 3 bits. That means there are 3 states that are not accounted for. This is an obnoxious error that only happens sometimes. Is it'll simulate, it'll work, it'll synthesize, and the next time you open Vivado, it'll throw a very obscure error that really just means, hey, you need when others. I don't know how it decides when you need to do the when others, and it's going to throw an error, or it's going to let you self-sabotage, right? Because again, if it's not, it doesn't care. And those are normally not a problem, but sometimes you end up with race conditions, right, that you would like to throw an error or go back to idle or something. Instead, it'll jump into one of those states and freeze up. And that gets harder to debug than if you have the when others condition. And in fact, if you want it to lock up, right, you might want to write something that is when others go to this state, freeze in the state, send out an error signal, right? You could add an error output and then like have a light that is tied onto your FPGA that turns on if you've broken something, right? This is the same thing concept as the debug. Sorry, the status lights is what I called them, right? In some of the designs that I've shown you. I really like anytime I'm designing a complex state machine to have status lights that at least tell me what state I'm in. Because if it gets stuck somewhere, those lights will freeze on and show me. The issue that you have to be careful with is that if you have states flashing through really quickly, it is impossible for you to tell the difference between always on and flashing through real quick. So sometimes you think it's stuck and it's not, which is why we like the Debug Core, right? I know at least 3 of you have started using the Debug Core, and it is your best friend or will be your best friend because this current state machine that you're working on is very complicated. And once you throw it on, you're going to well, you're going to run into some issues no matter what you do. So there's two things that I want to talk about with the last half of this class, really. And that's Debug Core, just to re-emphasize it, right? So that everyone remembers how to use it. And then how to use your oscilloscope to debug this problem. Like if you have problems in serial communication. It sucks that I have to do that, but I guess the whole COVID thing has interfered with everyone's learning of using oscilloscopes, but they are your friend. My recommendation to you, and I can't emphasize this enough because everyone does it, I've done it. If there is a cool tool that someone tells you about and your instinct is, oh, I don't want to use it because it sounds hard to learn, that's a good indication that you should just go learn it, right? Because we are all afraid of doing new things and we're like, well, if I don't have to, I'm not going to do it. And that's what, right, I think most people have done with the Debug Core is, well, I'm just going to sit and guess and check with my code. But I've had multiple people now that are on my side and they love the Debug Core because you find out how quickly it can solve all of your problems. The same is true for the oscilloscope. People would rather just sit and guess and check and hope that they get the right result eventually instead of hooking up your oscilloscope. So I'm going to cover both of these options so that hopefully I can spend less time with those types of problems and more time fixing other issues that you guys are going to run into. All right, Debug Cores first, since I'm already set up for that. So I've written, I don't know, a really bad version of a UART, I guess I would call it. And I actually really like to show this one. So, oh, I didn't even check if my Zoom is, okay. Share screen. I'm just going to screen, that should be fine. Okay, hopefully this is better for the recording. All right, first thing I want to point out here is I designed something bad on purpose here. So this is just a UART receiver that every so often is going to receive things, right? And needs to update the status lights. And I've done something right, which is I assigned status lights outside and I put it into this data hold, and data hold is updating. What I've done wrong is I processed on ready and then used this if ready event and ready is one terminology, right? Which is the same thing as writing rising edge. What I've done here is now tell this that ready is a clock. It now thinks that my ready signal is a clock, which means that it's going to use these special paths inside of the FPGA that are supposed to be designated for clocks. And you have only so many of those. Sometimes it won't be able to route those and you'll get these really weird error that are like error clock iBuff, clock underscore iBuff underscore obscure terminology can't be routed or something like that. What that really means is we don't know how to put this clock down. And what that often means is you have too many things that are clocks in one area. So we don't like to do that. So what we do like to do instead of this, right, is where I talked about you can create a pulse for exactly one clock cycle. And then you can each clock check and see if that pulse is true. And if it is, update. The only trick is whatever is sending the ready signal should be an inverted clock of whatever is trying to read it so that you don't have a race condition. Right? So for example, you have, and you can do that really easy. You don't have to invert the clock. You can just say if falling edge of, right? Because that will center the signal inside of that clock pulse. Anyways, that should be your target is a one clock pulse. Generally, that's the better design rather than trying to turn it into a clock. All right. Debug Core. When you run this synthesis, you can hit this set up debug. I'm just going to hit open design because I don't actually care. So you have to run synthesis first so it knows how to build the debug core, and then you'll hit the generate bit stream and it'll fix things for you. Or it'll freeze. Let's go ahead and run a new synthesis. Okay, well, I guess while this is going to take a little while to do, all right, I will talk about, all right, yeah, I'll just keep this going for a second and then. All right, let's wait for that and talk about using your oscilloscope to debug serial communication. So on your FPGA, you have these little PMOD ports, right? And you know what pins they're supposed to be. If you're looking end on, is it 8, I guess? 8. Sorry, just 6. And then these two are power and ground, so I don't really want to talk about those yet, just right. So like this might be your SDA, your serial data. And then this might be your clock, for example. I don't actually know what the order of these is for this particular device, but this is an in-out port, right? In the case of the I2C, and this is a clock. You only need those 2 wires because that's all we need. Now, what you can do is on this serial data line, you go and hook up one channel of your oscilloscope. On the other, you hook up the clock, right? So you have 2 channels on each of your oscilloscopes. You hook up 2. In the case of the SPI, there was a third one that would be of interest, right? Which is CS, chip select. The chip select is really nice if you have 3 channels, because the chip select is going to have this kind of framing effect where in the middle of this is where your data is. This is going to have a bunch of clocks, so on. And then in the middle of this, you're going to have data bits. Right? And I'm just, no, this would be a different row. I just want to overlap them so it's clear. And then what you would do is you could come in and you would trigger, right? You would set up your trigger to go on chip select. Because what that will do is it will freeze the oscilloscope frame relative to the chip selects, putting this in the middle. And then you can go look and say, make sure things like, oh, look, I'm in the middle of this rising edge of the clock. Yay. Or if I've done it wrong, oh, look, I've changed on the rising edge of the clock. You can literally go see that with your oscilloscope. Don't be afraid to do that. My advice is on the back side of these PMODs, right? The PMODs look something like this. The legs. Be very careful, be very wary of sticking your oscilloscope against these, because if you short together power and ground and actually slip it off, you could break that PMOD connector, or all of them, right? Because it has no impedance between 3.3 volts and ground, which means infinite current, which can burn out your voltage regulator. So don't do that. Just plug wires into the end of it and hook up your oscilloscope there. It's not really fast enough that it's going to matter. One other thing, there is a thing on your oscilloscope that limits the bandwidth. So be aware that you don't limit your bandwidth if you're going faster. So I think these oscilloscopes, if you put a bandwidth filter on, is like 20 megahertz or something, which is probably okay. but depending on how fast you're generating this clock, right, maybe it's not. In this case of I2C, you're fine. I don't think we can even go close to 20 megahertz. I think it's in the hundreds of kilohertz, but with the SPI, you can go up to like 28, I think, or 34 megahertz on the SPI clock. So anyways, on the I2C, it doesn't matter. There is a phenomenon that you guys should be aware of that I like to mention, because you guys don't necessarily know this. And I've had students working for me on senior projects run into this problem. This is a square wave, right, which means a very fast rise time, and it can only drive so much load, right, because there's the filtering effect of capacitive load. It turns out that the capacitance of these probes is something like 14 to 20 picofarads, somewhere in that range. And so when you measure, you may see something, well, it should be this, and instead does something like that. And there's actually ends up being an open question, because that if you see this, it can be one of two things. It can be either you're going too fast, right? That your whatever CMOS device is driving this is not sufficiently quick to rise and fall as fast as you told it to, or it is going fast enough, but the capacitance of your probe, when you touch it, is interfering with the measurement. So disconnected, everything is fine. Connected, it looks all wrong because you've added capacitive load. Be aware that that can happen, is that the act of measuring something changes what you're measuring, right? We know this to be true. And if you've like taken any of the quantum physics courses, this is very true, right? Depending of whether you're looking at something or not can change how it behaves. That's the form of measurement. When it's a physical measurement, it's extra true. So be aware that active measuring something can ruin the measurement. Okay, so in the case of this, SDA and clock, you're going to need to, so if we're not talking SPI anymore, remember that the serial data is sometimes being driven by you and sometimes being driven by the device, the ADC, okay? The ADC, however, only has a pull down network. It does not have a pull up network. It cannot drive to 1. So if this is your FPGA, and this is your ADC, draw it the other way. It looks like this at the output, where this can pull to 0, or it can just disconnect, right? It's either connected to 0 or not. That's how it deals with the its IO, right? Because you're in it IO, you're in in-out, it is also in in-out. It does it this way, is it just doesn't drive to 0. Now it can function as an input. So what that means is on your side, we're going to have an IO. It turns out the easy way for us to do this is a mux, where the select on the mux can be in-out. Where if I'm an input, I'm 0, and I go to high Z, and then this signal can come around and function as an input, right? Because a high Z means disconnected effectively. And then the signal can be used as an input, otherwise an output. But then in order to allow this, we need to help this go to 1. We're going to add a pull-up resistor. So that if we're driving a data and it is a 1, doesn't matter. 1 is 1, no current. If it's a 0, well, this is going to drive it to 0 easier than the pull-up resistor pulls it up to 1, right? Because there's no resistance when you're using a MOSFET as a switch, and there's a lot of resistance pulling it up. So the 0 easily overcomes this. The 1, it doesn't matter. It agrees. It doesn't pull it anywhere. And it turns out it doesn't matter as long as this one or this one is pulling it to 0, it is 0. Now, we can hook up our oscilloscope here and look at the signal, right? We don't have to have our ADC plugged in to look at the signal. and then we can trigger off of the clock, or the falling edge of SDA is probably a good one, right? We're going to set up a trigger, look at the clock and the signal, and then look at however many bits, and you can check and make sure that the data packet is right. So you can go look at your address, you can look at the acknowledge, you can look at everything, right? And make sure that they're doing what they're supposed to. And you know what they're supposed to do if you go look at the data sheet, right? So that's an important thing to be aware of, is you should know what the signal should look like. If you don't know what it should look like, you need to do more reading of the data sheet or soul searching or something, right? It's not a mystery. It's not like, oh, I don't know. We know that it should start with address, and then it should acknowledge stuff, and then so on and so forth. And we know what those bits should be. We can go look at it and make sure we're doing everything right without even plugging the ADC in. Now this, I will talk about in just a moment now that I fire it up, but the short of it is, I'll pull it up this way. So oh, I just turned off the camera. And then this case, I actually want to share my screen. Okay, so if I go and create a new, a new design source. Actually, I'm going to pause, because if I do that, then it's going to say synthesis is out of date, and we're going to run into the same issue that made me start this whole thing in the beginning. Okay, so sorry. I know this is stretching your brains a little bit. We're going to bounce back to setting up a debug core, and then I'll come around to how we use the pull-up resistor. So when you hit the debug core and set it up, it's going to pop up with this window. I just hit next. I already have a debug core that I set up, so I'm going to continue debugging the 13 nets, but I'll show you real quick. You're going to pop up with this window, nets to debug. You can either find nets to add if you know what their name is, or you can come over to this net list, but dragging it to the side and saying, well, inside my URRX top, there are these nets that I want to go look at. Or inside of my RX2, there are these nets that I want to go look at, right? Like maybe I care about bit count, for example, make sure that's working. All I have to do if I want bit count is drag and drop. Notice that my bit count is already over here, so it's happy and fine. I have bit count, P data. Remember, this is a UART receiver that I'm working with. RX, state RX. Well, the next obvious one that I probably need is the serial data, right? So this, and you'll notice that sometimes the ports are, or the nets are named a little bit weird. This SLI port 0, I'm just assuming, honestly, at this point, because I haven't looked at this design in a while. Data in is probably more what I'm looking for. Yeah, think data in. I just drag and drop. Boop. It is not accessible from fabric routing. All right, well, let's dive down a level. I've never had that error before, by the way. That was a surprise. Notice that I do have the state. Highly recommend putting the states in. There we go. Now I found that data in. It just wanted the buffered version. I guess everything is fine. I click next. Sample data is when I set up a trigger, just like an oscilloscope triggers on something, right? The debug core triggers on something. The trigger here is much more sophisticated because I can literally trigger on the state. I can say when the state is start bit, I can trigger and pause. This will give me a number of samples around it. So I'm just going to go with like 8,000. In the case of the UARTs, it kind of needs a lot, right? Because we're really slow compared to the system clock, right? The SPI clock and the I2C clock, the serial data clocks are going to be slow compared to system clock. So I need lots of samples to be able to see a broad range of things. I'm just going to click the capture control. I strongly recommend clicking that one. It's going to give you some options down the line. Advanced trigger doesn't really matter. You're not going to use it in this class, I don't think. So you hit finish. It's going to set up and build a debug core for us. That's going to be some logic that goes in and has these extra points that click onto these nets that I've told it to, and then provide them as an output over USB. That's what it's doing. Once I've done that and it's happy, I can go generate myself a bit stream. It's going to create the new implementation, right? So I created synthesis. I told it to add a debug core to that synthesis. And then I'm going to implement that for my specific hardware. And then I'm going to program it. While that's initializing, it's taking a long time, but that's okay. Let's bounce over. I have this other project pulled up. If I do this, create a new design source, which I'm just going to create a new file and call it blah. And I go and open blah. See this Unisim library? This is how we're going to go ahead and make the pull-up resistor. We're actually going to use the Unisim. Okay. I don't remember how to do that right now because it's rare that I do, but it's not too hard for me to bop over somewhere and search for Vivado Unisim pull-up. Primitive IO pull up. This looks like about what we want. It has a port called O. Direction is an output with a width of 1 as a pull up output. And it says we can connect directly to a top level port in the design. Okay, it's going to have an instantiation template where it's going to say, hey, pull up instantiation. It's going to call pull up and then port map O to O. Okay, well, all that means is, oops, if I have a port S data of in, if I'm going to call it standard logic, I need to there we go. I can bounce over and say pull up instance, pull up, and I'm just going to copy this. Hopefully it works. out. There we go. So this told us that it likes to be connected to an output. Just made it an out. It's fine. So now this O is the output or the bottom side of that pull-up resistor, which is drawn here, right? The bottom side of this resistor is the only port. And I'm just saying, go connect to this in out. That's all I need. Now I have a pull-up. Super easy. But you do need the Unison library. Notice that I didn't have to declare a component for this at all, because the component declaration is already handled inside of the Unison library. So I just need to create an instance of it. Okay. Bounce back here. Still optimizing the design. While we're waiting, I would like to remind you that in each of your projects, you can click the settings button, hit simulation, down here in simulation, and I can give it a default runtime, right? So that I don't have to tell it to rerun a certain amount of time. I just figure out one time how long my simulation should be, and I give it a default. This is very handy. Some of you are still struggling with running the simulation for the right amount of time, right? Remember that sometimes when you do it, just hit the full scale span because maybe you're just looking at the very end of it. And then you also need to zoom into the very beginning of it sometimes in order to make sure that you aren't zoomed out way too far, right? And keep in mind, you should know how long it should be, right? So if your clock period is 10 nanoseconds and you know it's SPI and you're gonna run for 16 samples, I just do 16 times 10 nanoseconds. That's how long I run, right? You should have an idea of how long it should take. Right, this just takes forever when you have a debug core, right? That's the big disadvantage of the debug cores. But I promise you, I would be astonished, just astonished if any of your state machines worked the first time you did it. I've not seen it yet. I'm not saying it's not impossible. Some of you are actually doing really well with the code, but I would still be very surprised if any of you got it right the first time. And it turns out the debug core is much easier than using the oscilloscope, because the oscilloscope tells you nothing but what's on SDA, right? Whereas the debug core can tell you any of your internal signals as well, which is very handy, especially the state, right? Because that's usually the biggest issue. But the oscilloscope, you're going to need both, because you're going to need to use the oscilloscope to make sure that the acknowledges look correct. Because that's a big one, right? Because you're having to switch between in and out mode in order to read the acknowledges from the ADC. Don't make the mistake of confusing the two different types of acknowledges. There is an acknowledge from the ADC, and there is an acknowledge from the FPGA to the ADC. So some of the acknowledges are ins, some of the acknowledges are outs. Fortunately, if you mess them up, I've not seen an ADC or FPGA break in this case. Even when you drive 1 to 1 and the other to 0, when you make that mistake, it shouldn't break them. They're pretty robust. But do keep that in mind, because if it's not getting the acknowledges, it's not going to work, right? Okay, we're writing the bit stream now. It shouldn't be much longer. If you don't know for some reason yet, in the top right, it tells you what it's currently working on. While I'm waiting for that, anytime you have an error, I want to point this out again and again and again, because you guys still are struggling with debugging. When you get an error, I always go to the TCL console, because it turns out to be more useful than the messages most of the time. And what you do is it's going to have red errors, right? What you do is you scroll up just a little bit usually and find the black errors, and there's going to be the same number of black errors as our red errors most of the time. And the black errors are the most descriptive, and then you can scroll to the far right and they will tell you which file and the line number that the error occurs on. Once you have the line number, it is usually that line or the line before it that is causing the problem. If the line number points to the begin or like a process of or something, it can be anywhere in that process, which is a nightmare to debug. That's the worst, but you just start looking at like all of the ends for the process and see if you have the begin, things like that. Okay, so now I can program my device. Once I program my device, it's going to pop up with this type of window, which is super helpful. I can hit the run button to run the trigger for the core. But in order to make it work really well, I need to set up triggers, which I made go away, and I always hate trying to find them. Oh boy. You. Sorry, I don't know what happened to my trigger window at the moment, and I don't remember how to pull it back up. Log reports, dashboard. Oh boy. Okay, let me try and close my debug core and relaunch it and see if that fixes it. Oh, there it is. Okay. So here we can trigger on things. So right now I have it set up to trigger on stateRx if the value is not equal to 0, right? So I happen to know that my state idle is 0. What I'm trying to trigger on is if I leave idle, then it triggers, okay? I can also add other ones that I would tell it which signal that I want to be on. So I might have something like, I want to trigger on data in, and I want to trigger if it is equal to 0, right? In this case, it's a UART, which makes sense why I would want to do that, right? Because the UART should start high, and if it begins, it should drop to 0. This is my receiver, so I'm going to see what happens, supposedly, when I send it a signal. Unfortunately, I'm out of time, and I don't really remember how to make my waveform window come back. I'm sure it's there. Here we go, waveform. Come back. Okay. So now I should be able to hit run trigger for this core. And it's not finding anything happening. So I'm going to bounce over to this. I've set up my serial. I'm going to send a character, and it's not triggering. So I guess I probably set something up wrong. As I said, I programmed this UART way too quickly. Yeah, I'm actually really surprised it's not capturing that. Anyways, that's how the debug core is going to work. Okay, is you're going to tell it a state that you want to be in, or a situation that you want to trigger on, which is likely going to be a state, and just say it's equal to this state, freeze, and let's go look at what we're doing. So you might be like, if the state equals acknowledge, let's go see what we're doing with all of these internal signals. If we're sending too many bits, too few bits, maybe trigger on your bit counter or whatever it happens to be. I'm sorry this didn't work. I'm not quite sure what I set up wrong in my UART. And now I've apparently frozen my Vivado, so that's cool. Oh, there's one more thing that I want to show. Sorry, I forgot. Is on the debug core, there's this button that sets the operator. So what you saw that I have 3 triggers set up. I want them to be global or. I want any one of those, right? You could also do and. So I could say if I am not an idle and S data is 0, for example.
Right. But you need it to trigger on both, or you trigger
Yeah.
on both of them.
Yeah, we don't have a homework test and a lab due on the same day.
I'm rushing to, last time I'm pretty sure we did. So.
Oh, yeah, I texted him, I emailed him like 2 days ago or last night. Learned like, hey, can I do this next week? He's like, it's due next week.
I'm ready to start for also, but I have to do the, I did it thanks to Chris.
Yeah, I looked at the practice.
All
That's
this
a pretty
other
good
stuff, I'm, it's beyond me, but I can explain the other stuff, but not the offense.
Well,
Yeah,
have done, then I can
Sure.
look at it and see if I can
oh,
figure
and
out
I
something,
I tried putting, I highlighted, so for the map, the block diagram, I highlighted what went where for you.
but- Oh.
If it's right, I don't know if it's right or not. So you
That's
can
getting me
maybe
more points
see,
than I
oh,
can
that's
do
where
right
that
now.
went. Maybe what I got.
Cool. Thank
This
you.
class, you don't have a state code. Stop it.
Uh,
Not in your graph that you're making.
See you later, guys.
It would be good, so you have the jump for that.
Rob, 9.
Yeah, do that. Study group?
Tomorrow at 9
Yeah. Cool, where at?
here.
Cool.
All right.
Thanks.
Yeah, Trent.
We'll have study review full test, study after class. Lab test, so.
Right now, I really wish Halloween weekend wasn't right before the exam. I wanted to study all weekend, but also I wanted to party. But I can start doing right now.
Okay, so I guess it is simply not leaving idle for some reason,
I get out of flow.
which it could be a reset issue.
Given, I think it's on target.
Reset is active high. If reset is 0, then we're gonna reset, and then you are top
Is there, when's the next one?
reset.
Here, except for, this is empty until then.
Oh, there's empty till 12:40.
That's because I have.
Reset is not active high, but I'm not using it anywhere else. So Sorry, I'm still recording on the audio so that if anybody wants to watch this video and me stumble through figuring out why it's not working, they can. So I can run immediates and I get the samples, but I'm still in idle.
So mad.
It is just not leaving idle no matter what I do. What's sad is I swear I ran this before and it worked. Is it, I guess maybe this process is the issue. Do you have a question?
Yeah, I can wait.
Yeah, it's okay. I'm gonna stop the recording now because I'm not quite sure what's going on with it, and it's probably just a bug in my code.